Section. Introduction. We're here to discuss large language models, LLMs, which have shown impressive performance across a variety of tasks due to their ability to learn in context, ICL. These models can handle everything from understanding natural language to reasoning and planning. However, they're not without their challenges. They require a lot of resources for training and deployment, can be slow, and are prone to making things up, a phenomenon known as hallucination. On the other hand, supervised task-specific language models, SLMs, are more cost-effective and faster, but they lack the ability to handle multiple tasks. Because they're smaller and cheaper to train, SLMs can quickly adapt to specific tasks and learn task-specific knowledge. This makes them particularly useful when new, custom tasks come up in real-world applications, which can pose challenges to LLMs that are out of their training distribution, OOD. Even with their ability to learn in context, LLMs often don't perform as well as SLMs on natural language understanding tasks, especially when they're out of their training distribution. They're also more likely to hallucinate when completing classification tasks. Most research treats LLMs and SLMs as separate learning methods, but we believe there's potential for them to work together. This brings us to our main question: can SLMs improve the performance of LLMs? More specifically, can SLMs help LLMs handle out-of-distribution scenarios and reduce hallucination? Some previous research suggests that a smaller, task-specific language model could help improve the performance of a larger model, but this hasn't been thoroughly explored. To investigate this, we conducted a series of empirical evaluations. We believe that SLMs and LLMs can complement each other. SLMs have task knowledge from supervised training data, while LLMs have domain knowledge from large-scale pre-training. We focused on out-of-distribution tasks for our evaluations. In this paper, we introduce SuperContext, a simple and versatile learning strategy that uses small models to improve large models, especially in out-of-distribution scenarios and in terms of factuality. SuperContext integrates the outputs of SLMs, which represent supervised knowledge, into the prompts of LLMs. This is similar to existing methods that retrieve information from external knowledge bases or API tools, but our goal is to improve task adaptation, not knowledge acquisition. Instead of search engines, we use SLMs as consulting agents. We tested SuperContext in 2 experiments and analyzed it from 2 perspectives. The first experiment involved out-of-distribution natural language understanding, where we used the supervised knowledge from task-specific models to improve LLMs. The second experiment involved question answering with unanswerable questions, where we used SuperContext to reduce hallucination. We also built an interpreter to explain why SuperContext outperforms traditional in-context learning methods, and conducted extensive quantitative and qualitative assessments to understand how small models can help large models with classification tasks. We tested SuperContext on both zero-shot and few-shot settings of natural language understanding and question answering, using the out-of-distribution benchmarks GLUE-X and the question-answering dataset Squad 2.0. Our results show that SuperContext significantly outperforms both LLMs and SLMs on 9 different tasks in out-of-distribution settings. To our knowledge, this is the first work to systematically integrate SLMs into LLM inference decisions, which significantly improves the performance of LLMs, especially in handling out-of-distribution data and reducing hallucination. In the next section, we'll discuss in-context learning, which is a key part of large language models. We'll provide in-domain data for several natural language understanding tasks, each with 16-shot examples. We'll denote a question-answer pair as x_I, y_I, and the index set of in-context learning samples as s_j, where n is the number of shots. The few-shot examples are denoted as x_I, y_I, where I is in the set s_j and n is the number of problem instances for the task. In traditional in-context learning, the probability of a large language model generating a response y_j when prompted with the few-shot examples and the discriminative model's prediction, confidence, and the special prompt s_I is approximately the same, regardless of the exact choice of the few-shot examples. We'll consider both zero-shot and few-shot settings in this work. The choice and order of the examples can significantly affect the test performance. To reduce this impact, we'll use a method called thrice resampling with replacement to compute the average results. The key to designing alternatives for in-context learning is to find the right knowledge to embed into the decoding process of the large language model. Recently, a contrastive decoding approach was proposed that uses the differences between expert and amateur language models of different sizes to choose tokens that maximize their log likelihood difference. This approach generates high-quality texts with the help of an amateur model. However, it still requires mapping between the two models during training, which can be tedious. Section Summary. Large language models, LLMs, have shown impressive performance across various tasks but come with challenges such as resource requirements, slow inference times, and hallucination. On the other hand, supervised task-specific language models, SLMs, offer cost efficiency but lack general multitask capabilities. This paper introduces SuperContext, a strategy that integrates SLM outputs into LLM prompts to enhance performance, particularly in out-of-distribution scenarios and minimizing hallucination. Empirical evaluations demonstrate that SuperContext significantly outperforms LLMs and SLMs in various tasks, contributing to more reliable and factual deployment of LLMs. Section. SuperContext. We're introducing SuperContext, a straightforward and versatile method for in-context learning. This method combines the supplementary knowledge from a small, discriminative model with large language models, LLMs, to make predictions for new tasks. This is achieved by merging guidance and the prediction from a fine-tuned, small discriminative language model. In our approach, we insert our receipt, which we'll call R_I, between the question-answer pair. This receipt serves two purposes. It provides the prediction and confidence level from the discriminative model, and it further explains the prediction by asking the LLMs to identify which in-context example it learned from and which rationale is important. We illustrate this process using the sentiment analysis task as an example. Throughout this process, we don't use any labels from the corpus Y as demonstration examples, which is consistent with real-world scenarios where typical data points are out of domain for the model. The training set and in-context examples are both taken from the in-domain dataset. The training set is used to fine-tune the small language model, SLM, and in-context examples are used as the prompt. SuperContext also includes an optional component, the interpretation prompt, which should be inserted between the input prompt and test example. The output is expected to include the index of influential in-context examples and the rationale used when making the prediction. SuperContext operates on the assumption that the method can be represented as a given LLM of X_I, R_I, Y_I, for each problem instance for the task, and S_I is the optional prompt defined as the instruction of the interpreter. The probability of generating the response, Y_J, is approximately invariant to the exact choice of the few-shot examples. We summarize the SuperContext augmentation method in Algorithm 1. The discriminative model is trained on the in-domain dataset and tested on the out-of-domain corpus. For in-context learning of SuperContext, Y_J is prompted with the concatenation of the few-shot examples with the discriminative model's prediction, confidence, and the special prompt, S_I. The output should be the prediction of LLMs towards the test case with interpretation if available. We selected Electra Large as the SLM for natural language understanding, NLU, experiments, and Roberta Large for question answering, QA. For evaluating the performance of SLM-enhanced LLMs, we selected ChatGPT and Llama 2-7B Chat as backbones. We considered 7 classical NLU tasks: sentiment analysis, natural language inference, paraphrasing, question answering NLI, textual entailment, textual similarity, and linguistic acceptability. We sampled 3,000 examples from GLUE-X for each out-of-domain dataset and ensured that in-context samples are extracted from different domains of test sets. For NLU, we considered 2 in-context learning methods as baselines for ChatGPT and Llama 2-7B Chat, namely 16-shot ICL and BM25. The 16-shot ICL method randomly extracts few-shot examples from the in-domain dataset as the demonstration prompt, while plus BM25 represents the dynamic in-context example selection method using BM25 to select the top 16 examples that are similar to the test case. We also present the ablation that leverages SuperContext with the optional interpretation prompt, shown as plus interpreter. The variants of the backbone model are kept the same between ChatGPT and Llama 2, namely, plus BM25, and plus 16-shot. Due to the relatively low instruction following ability of Llama 2-7B Chat, the plus interpreter is not explored in experiments of Llama 2-7B Chat. Due to the difference in the instruction following ability between the ChatGPT and Llama 2-7B chat, we insert the 16-shot in-context examples appended with the prediction and confidence of SLMs, namely SuperContext, 16-shot. Different from NLU, the question answering task is evaluated by the holdout test. The in-context examples are extracted from the training set and LLMs are evaluated on the validation set. We establish the baseline by using cluster plus filter method. In particular, we adopt mini-LM to encode the training examples and build a union find set. Then, we use the cluster and filter pipeline to retrieve the most relevant examples with the test sample as in-context demonstrations for ChatGPT. For Llama 2-7B chat, we adopt two fine-tuned methods as baselines using multi-turn and single-turn tuning on 1.2 epochs, respectively. Section Summary. The SuperContext approach incorporates auxiliary knowledge from a small discriminative model with language models to make predictions for new tasks. It uses a prompt design that includes the discriminative model's prediction and confidence, as well as an optional interpretation prompt to explain the prediction. The SuperContext augmentation method involves training the discriminative model on an in-domain dataset and testing it on an out-of-domain corpus, while the in-context learning of SuperContext prompts the model with few-shot examples and the discriminative model's prediction. Section. NLU results. In our study, we found that SuperContext consistently outperformed other models in natural language understanding tasks, as detailed in our results table. When compared to both SLM and LLM, SuperContext showed superior average results, highlighting its exceptional performance. We also experimented with using the Electra large model to enhance the performance of Llama 2-7B chat. This not only surpassed the performance of ChatGPT but also matched the SuperContext based on ChatGPT. This suggests that it has a significant ability to reduce inference costs. It's important to note that the data size used for ChatGPT and Llama 2-7B chat varied, which led to different results for SLMs. With the aid of 16-shot in-context learning, ChatGPT's performance improved, but it was still lower than SuperContext. Our method outperformed 16-shot in-context learning with a much shorter input sequence length, roughly 30 times shorter. We also tested SuperContext with the prompt of the interpreter, which required LLM to recall influential in-context examples and provide rationales when making predictions. We found that including model confidence in the prompt led to significant improvements in average performance for both ChatGPT and Llama 2. However, for QNLI and QQP tasks, Llama 2 without the SLM's confidence achieved the best performance among several methods. Our results also showed that the interpreter did not bring significant benefits when compared to SuperContext in most tasks, except for a slight improvement on QNLI. This could be because the explain then predict prompt may not be suitable for incorporating with SuperContext, leading to information overload. In addition to ChatGPT, we compared SuperContext with several baselines based on the open-source model. Experimental results showed that SuperContext with 16-shot in-context examples achieved the best results on 7 of 8 tasks included in GlueX compared to Llama 2-7B chat under the same setting without the help of the small model. Interestingly, it outperformed Electra large in terms of average performance. This significant performance increase indicates that SuperContext improves the NLU capability of both Llama 2-7B chat and Electra large simply and effectively. On the task level, we observed that both ChatGPT and Llama 2 had lower accuracy than expected on multiple tasks. With the help of SuperContext, results could be improved significantly. We also evaluated LLM's ability to minimize hallucination on the QA task based on Squad 2.0. We found that although the original ChatGPT achieved the highest accuracy for deterministic questions, the exact match and accuracy for open questions could be significantly improved by SuperContext. We observed that the fine-tuned methods could significantly improve the rate of valid JSON. Despite fine-tuned methods outperforming the original Llama 2 chat and the in-context learning version, SuperContext achieved the best performance in terms of the M and accuracy for no-answer questions. We observed that the original Llama 2-7B chat model struggled with format adherence and hallucinations, especially in answering no-answer questions. However, when applying in-context learning with a mix of no-answer and has-answer instances, we noticed an improvement in handling no-answer questions, though this came at the cost of reduced accuracy in has-answer questions. Section Summary. The NLU results show that SuperContext outperforms both SLM and LLM models in terms of average performance, demonstrating its superior capabilities. Additionally, the inclusion of model confidence in the prompt significantly improves the average performance of both ChatGPT and Llama 2, while the interpreter only slightly improves performance on the QNLI task. In terms of task-level analysis, SuperContext improves the NLU capability of both Llama 2 to 7B Chat and Electra Large, and using BM25 to retrieve relevant examples enhances in-context learning performance. Finally, SuperContext improves the accuracy and exact match for open questions in the QA task, outperforming in-context learning and fine-tuning methods. Section. Reversed predictions. We've been studying the differences between the final predictions made by large language models, LLMs, and those made by small language models, SLMs. Our findings show that in about 3.02% of cases, the predictions made by ChatGPT were changed during the inference phase when using SuperContext. Interestingly, 57.88% of these changes were corrections, suggesting that the references generated by SLMs can help improve the natural language understanding capabilities of LLMs. When we used SuperContext on Llama 2 to 7B Chat, we found that it was less likely to change the predictions made by SLMs, only about 0.5% of the time. However, when it did make changes, it was more likely to correct the SLM's predictions than to make random guesses, 52.13% of the time. We also wanted to understand why SuperContext performs better than traditional in-context learning methods. We looked at two things: how LLMs recall concepts and rationales they've already learned, and why they struggle in out-of-distribution settings. We found that both ChatGPT and InstructGPT pay different amounts of attention to different in-context examples. For instance, ChatGPT with 16-shot examples tends to pay less attention to examples as they appear later in the sequence. The second in-context example was focused on over 35,000 times, while the last example was only focused on around 5,000 times. InstructGPT, on the other hand, showed a U-shaped pattern of attention, focusing more on the beginning and end of the input context and less on the middle. This is consistent with previous findings that model performance drops when models have to access relevant information in the middle of long contexts. We also looked at the rationales generated by LLMs when making predictions. We found that SuperContext had the highest average overlap between human and model rationales, after removing stop words, with a score of 0.575. The 16-shot ChatGPT only achieved a score of 0.45. We also found a positive correlation between the confidence of SLMs and the performance of LLMs. Both ChatGPT and Llama 2 to 7B Chat showed this correlation, suggesting a high level of consistency between the models. We found that most instances in our GLUE-X dataset received the highest confidence interval from 0.9 to 1.0, and these instances could be predicted with significantly higher accuracy than others. When comparing the performance of GPT 3.5 and Llama 2 to 7B Chat, we found no significant difference for instances where the SLM's confidence was less than 0.6. However, when the confidence was more than 0.6, GPT 3.5 performed substantially better. In conclusion, our findings suggest that SuperContext outperforms both SLMs and LLMs because it takes advantage of the high consistency in discriminative models and the complementary properties of recent generative models. Section Summary. The study compares the predictions of language models, LLMs, and super-language models, SLMs, and finds that using SLMs improves the NLU capability of LLMs, with 57.88% of overridden predictions being corrected. The analysis also explores how LLMs recall learned concepts and rationale from pre-training, and highlights the importance of SLM's confidence in communicating task knowledge to LLMs, showing a positive correlation between SLM's confidence and ILM's performance. Section. Related work. Let's talk about the related work in this field. The concept of in-context learning, which is the ability of a language model to understand instructions and perform complex tasks without supervision, was first introduced by GPT-3. This idea has been further developed by incorporating additional knowledge or reasoning instructions into the prompt, as seen in methods like chain of thought, COT, and tree of thoughts, TOT. However, these methods can be time-consuming and costly, especially if we were to apply them to a model like GPT-4. Our approach, on the other hand, is more cost-effective as it only requires a small amount of supervised knowledge in the prompt. There have been various attempts to improve in-context learning performance. Some have focused on creating demonstrations, others have explored different methods of selecting examples, and some have even looked at the order in which examples are presented. The contrastive decoding method uses a smaller language model for assistance but requires additional computation. In contrast, SuperContext has shown superior performance on out-of-distribution (OOD) test data in a cost-effective way. Our work also relates to efforts aimed at understanding and explaining in-context learning from various perspectives, such as implicit Bayesian inference, pre-training data, and information compression. Different interpretations of in-context learning and real-world natural language processing (NLP) tasks have been proposed. The interpretation part of SuperContext seeks to explain how large language models (LLMs) recall in-context examples and produce rationale. The use of external knowledge as supplementary information to help LLMs provide accurate and timely responses is a recent trend. Traditional methods require a knowledge retriever to guide the generation of responses. The source of this external knowledge can range from local documents to the entire internet. LLMs can also use special plugins to enhance their capabilities, such as Toolformer and LangChain for calling external APIs, and Hugging GPT for planning tasks. Previous work has either relied on web information and search engines for external knowledge or performed planning tasks outside the NLP scope. However, these studies lack an interpretation part to explain their reasoning. SuperContext shares some similarities with Hugging GPT in terms of using language model architectures. However, our approach differs in its application and analysis under out-of-distribution (OOD) conditions, an area that has not been extensively explored in existing literature.